This problem from Chapter 7 deals with calculations related to photons and energy. Take a few minutes to read the problem, understand the question, prepare a solution, and then work on the problem. Once you have finished working on the problem, have a look at the answer that will be displayed shortly. In this problem, the key information is that we have a certain minimum energy that is required for something to happen. In this case, send an impulse to the brain. And we also know that we have red light, which is 700 nanometers in wavelength. So the plan is, first we're going to calculate the energy per photon for red light using the equation E equals hc over lambda. Second, we are going to dig out constants if they are not provided and keep an eye on the units that are used. And finally, we are going to determine the number of photons based on the minimum energy that was stated in the problem, which is 2 times 10 to the minus 17 joules. So let's use that equation first. So epsilon equals hc over lambda. H is not given, so we are going to have to find that out from a textbook or will be given in an exam. And that's 6.626 times 10 to the minus 34 joules second. We also need the speed of light, which is 3.00 times 10 to the 8 meters per second. And we also will need to convert 700 nanometers to meters. And we know that 1 nanometer equals 10 to the minus 9 meters. So this number is 7 times 10 to the minus 7 meters. So what we will do then is replace those values in the equation. Keeping an eye on the dimensions that we are using. We cross out meters and meters. We have seconds and seconds. And that gives a total of 2.8397 times 10 to the minus 19 joules. So the next thing that we need to do is, given that amount of energy that we have for that particular wavelength, we need to calculate the number of photons that are required for that. So we can say from this then that one photon has an energy that we just calculated, multiplied by the number of photons that are required to trigger the process, which are 2.0 times 10 to the minus 17 joules, gives a total of 70.430, which rounding up means 70 photons. And this should be the answer to this problem.